The topic of today's lesson is elastic potential energy. Elastic potential energy is energy that results from an object being either stretched or compressed. Stretching makes an object larger, and compressing makes it smaller. Some examples of elastic potential energy are an archer shooting an arrow, a snake in a can prank, or a snowball being launched from a slingshot. Elastic potential energy comes solely from how far back an object is stretched or compressed and the strength of the object. To look at elastic potential energy, there is some necessary background information. Right here, I have 5 springs that appear identical other than the color. My assistant will now put an identical 2-pound weight on the bottom of each one. What you should notice is that some of them stretched more than others. This is because some of the springs are stiffer. The spring constant, or K, tells us the stiffness of each spring. K is measured in Newton meters. The spring constants are 50 Newton meters for green, 40 Newton meters for white, 35 Newton meters for yellow, 30 Newton meters for blue, and 25 Newton meters for red. The green spring stretched the least because it has the largest spring constant. The next step is to calculate the change in length of the spring. Initially, this spring has a length of x sub 0. In this case, it is equal to 25 centimeters. Now we will add weight to the spring. We can now write the new length as x sub 1, or the final length. The final length, in this case, is 49 centimeters. From these two measurements, we can find the amount that it is stretched, or delta x. Delta x equals the final length minus the initial length. So, as a result, we should get 49 centimeters minus 25 centimeters, which means that our delta x is 24 centimeters, or 0.24 meters. Now we can analyze the formula. Elastic potential energy equals 1/2 K delta x squared. As we discussed a few moments ago, K is the spring constant, or stiffness, which is measured in Newton meters. Delta x is the amount that the object is stretched or compressed and is measured in meters. If the object is compressed, delta x will be negative, and if the object has been stretched, it will be positive. Since delta x is squared, the sign has no bearing on the amount of energy. The unit for all of energy is joules. To understand the formula, we will look at the simple act of shooting a rubber band. Pulling it back makes it go further. This is because increasing the delta x results in more elastic potential energy. Additionally, if you use a thicker rubber band, you don't need to stretch it as far so that it will travel the same distance. This is because a thicker rubber band has a higher spring constant. Now we will look at a few example problems. The first question is: a medieval archer draws back the string on his bow 0.65 meters. If the string has a spring constant of 350 Newton meters, how much potential energy does it have? A good place to start is by writing down the information of the problem. The string being drawn, 0.65 meters, means that delta x is 0.65 meters. The next piece of information is the spring constant, or K, is 350 Newton meters. Since we are asked for the elastic potential energy, we should write down the formula. Elastic potential energy equals 1/2 K delta X squared. We can now plug in 350 for K and 0.65 for delta X. If we now multiply, we should get 73.9 joules, which is our final answer. For the next problem, your friend is shooting a rubber band with a spring constant of 15 Newton meters at you. Prior to stretching, it has a length of 0.1 meters, and after stretching, it is 0.22 meters. How much elastic potential energy does it have? Again, we should begin by writing down the information in the problem. The spring constant, or K, is 15 Newton meters. Delta X equals the amount the spring is stretched. Since it started at 0.1 meters and is stretched to 0.22 meters, the delta X should be 0.22 minus 0.1, or 0.12 meters. Since we are asked about the elastic potential energy, we should write down the formula. Elastic potential energy equals 1/2 K delta X squared. We can now plug in 15 for K and 0.12 for delta X. If we multiply, we should get 0.11 joules, which is our final answer. If you found this video helpful, please click on the like and subscribe buttons below or visit us at rexwellphysics.com. Thank you and have a nice day. Bye!